The next talk is going to be by Eberhard Bodenschatz at Max Planck in Göttingen, and tell us about inertial particles.
Yes, so let me thank the organizers for having me. And I've tried to put together a talk which is slightly different than the typical talk you've heard from me. And so I'm going to talk about work that was done together with Haitao Zhu and Mathieu Gibert, and just to show you who we are. So this is my group at the Department for Fluid Dynamics, Pattern Formation, Nanobiocomplexity Complexity. I'm only talking about this part here. I'm not talking about the other 50% of the group. And the people doing the work is Mathieu and Haitao, and they have been doing these experiments, and this is our experimental hall where we have the turbulence experiments in it. Since at the conference we started to have some experiments on pressure measurements in turbulent flows, and I wanted to note a paper which is basically not cited, but which I think is actually interesting, because it's what we did is we used cavitation. I mean real-world cavitation, not just bubble tracking. We actually used cavitation to measure the pressure fluctuations in a large Reynolds number turbulent flow of a French washing machine. And there's data there which I would love to see compared with numerical simulations. And so I just wanted to mention that, because this paper is not many people have that on the search screen. I didn't want to talk about this, so what I will do is I will talk a lot about Lagrangian particle tracking. What we do is we do the most brute force technique, which is direct optical imaging of very small particles into flow. And recently, Haitao, so this is a typical projection of particle tracks that we are tracking by our techniques. And what you realize is when you look at these tracks for the papers until about a year ago or 1.5 years ago, what you realize is when you look in here, you have the tracks over here, and then our tracking procedure, as soon as we had lost the particle in our 3D fitting procedure, then we decided it's a new track. And so our tracks had very big gaps. And these big gaps we didn't know how to fill until Haitao had the idea of going into 6-dimensional space and saying that if I know the trajectory going up to this point, I know the trajectory here, but I also know the velocity at this point, and I also know the velocity at that point, and then I can go to in 6D space, and 6D space is sparse. These three have what looks full here is totally empty, and so you're basically looking in an empty space, and then you can connect the trajectories. And so Haitao wrote this up and just published this in Measurement Science and Technology in 2008. And sure enough, these red spots are the continuous straight line connections. So all it really means is we are missing the trajectory for a certain time, and then we pick up the same trajectory. So we're missing some data in between. We don't have that, but we can definitely then connect the thing and make large tracks. And so that's why I would like to talk first here about turbulent relative dispersion. And I know that Greg is going to talk about this in great detail. And so, well, you promised. And so what you're doing, what we did was this experiment where we look at the separation of two particles as a function of time. And at the time, we were hoping to see Richardson dispersion. And of course, being in Cambridge, this was what was proposed by Batchelor. Batchelor basically said that depending on your initial separation, you should have a typical time scale, which I call Batchelor time scale, for which the dynamics is ballistic. Basically, it just says the particles are moving out ballistically, depending on the scale you're looking at. So you're looking at a certain scale. For a certain scale, there's a certain time scale. For that time scale, things should be ballistic. And the important thing is that this C2 is the second order structure functions. You can derive this by an expansion, and you can really calculate, and C2 has been measured many, many times. And so what that means is you have a quantitative description of this prefactor, which also depends on epsilon and of course the initial separation. I don't know why this should be a capital R here, over here. Okay, so what we can do is you can find agreement with this prediction. This is the number. It's just calculated, and what we find, yes, indeed, we find a straight line for different initial separation, for different Reynolds numbers. You can plot this actually corrected for the slope. You see that it fits quite well. You can also show that the time scale should not be tau eta, but it should be T0. That's all in the science paper. But let me just show the data that we ended. So Grisha, what we did is we tried to find the r to the 2/3 scaling of Richardson. And Grisha proposed not to plot just the r minus r0 squared. We should actually just plot r to the 2/3 minus are 0 to the 2/3. And what we found was that if we plot this and we correct this by the property by T0, by T in the right way, what we find for different sizes, now for a given Reynolds numbers, what we see is that indeed the data turns over up here in this region. So this was in the science paper, but now we can do this better. And we can actually, since we have now longer tracks, we can now follow the particles for longer tracks, which means we have better statistics in this region, which we didn't have before. And so what that means is now these are the new lines, and indeed what we find is that there's a pretty good agreement over there. And so what you can do is you can say, let's take these peaks of these curves, which we published here in New Journal of Physics. If we take these peaks and we follow, I should also mention that this work was done with Nicolette, who is now at Yale. And so if we follow these peaks and just argue, well, how would these peaks change as a function of Reynolds number? So what we really do is we plot these peaks as a function of the scale separation. So this is the eddy turnover time over T0, which is the Batchelor time scale. So this is all the data for different initial separations, for different Reynolds number, all plotted on one plot. And what you find is that indeed, and PK, I should mention, has done the similar analysis in numerics. And what you find is, well, indeed, this thing seems to flatten out somehow. And so the question is, will it ever flatten out? I mean, will you ever see, a property which is independent of the initial separation? I'm not talking about the power law. I'm talking about the property of being independent of the separation, which is this intrinsic stochasticity that Greg will talk about. That's really the question here. It's not just the power law. So what are we doing? So the question is, do we get up here? And now I make a little bit of an advertisement. And so what we have done is we are building right now this wind tunnel in Göttingen, which hopefully is operational soon. We had a little problem with the heat exchanger, which leaked. And so let me just show you how this looks like. Depending on the prefactor that Christoph was talking about, depending what number you put in there, you can get R lambda between 6,000 and 9,000. It really depends on this energy factor there, on this prefactor in front of U cubed over L. And the active grid wind tunnel can have anything between 0.9 and 0.5, and you just don't know where you will be landing. And so we haven't done the measurements. Here's how the system is set up. So here we have the sulfur hexafluoride stored. This tunnel is filled with 9 tons of sulfur hexafluoride, and then we just pipe this in. Over here we have also another pressure vessel to do smaller experiments, and so we can provide basically a liquid with a very low kinematic viscosity. That's all we do, and this way we can reach high Reynolds number. By the way, this is an old tunnel from Prandtl, which we are also resurrecting. It's the only thing that's left over from the old institute, and so we will do that. And so let me talk very briefly about the exit time statistics. Now, are we doing in time? Okay. So actually, Luca and Feta and Sokolov did this in 2002, and then later Luca looked at it in numerical simulations. And let me show you newer data that we have taken. And so the question was, can you disentangle? So if you look at the Richardson dispersion, that we look just at the separation of particles. Here what we do is one basically takes a fixed thresholds along these particle trajectories when they move apart, and you ask yourself, how long does it take to move out of the volume, to move out of this distance Rn? So you basically fix some thresholds. You have initial separation R0. Then you take rho to the n, where rho could be anything where n is 1, 2, 3, 4, and rho, if it rho's 2, then you get basically get a doubling time. It just doubles, the distance doubles, and so you ask yourself, what is this average mean exit time statistics? And when you look at Luca's paper, what they showed was that here we have the this exit time as a function of of R for different initial separations. And so what you find is that this is the R to the 2/3 scaling, which you can asymptotically theoretically predict by some assumptions. And Luca concluded there's not a big difference on initial separations. And then over here, this is the Batchelor, this is the Richardson constant, which you can calculate also out of this like this. And what you see is in all the data, there was a little plateau. So let's see how our data looks. Now, please notice that this is plotted against, here this is plotted time. Scales are always scaled in eta, and times are scaled in tau eta. And so if we do that on our data, what we find is that indeed we find a behavior. Now this is the plot for G. And so what we find is that indeed we see a plateau over here. but then for different initial separations, which are quite large, by the way. I mean, these are 5 millimeters. So this goes from about 30 eta to about 120 eta. So it's very large separations. And what you find is different. Now, what you can also do is you can plot this in different, normalized by the separation instead of eta. Then you find another plot which looks like this. But again, you see the strong deviation, strong dependence on initial separation. Then what you can do is you can plot the separation time in terms of tau eta versus r in eta, which is exactly the plot that was in your paper. And then what we find is that, well, you know, the data kind of goes asymptotically up to this point. It actually looks very different from what was in the numerics. I don't know why, but it's just that's you do.
I think I know.
Okay, you can ask me later, so you can give a comment. Okay, now if we plot this as a function of r over r0 and you know, over t0, so the Batchelor time scale, then actually all the data collapses for the small scales, but not for the large scales. And you know, asymptotically, you could argue, well, in T there's this power law, but again, you see that it depends on the initial separation. So this is basically the power law seems to be there, but the initial separation dependence doesn't seem to go away. And it would be nice to see that. Okay, you can do that for other rows. So this is 1.05 instead of, and we went up to 1.11, and you did, I think, 1.2 in the numerics. So we can do this. Okay, so let me go on to the actual topic of my talk, which was to look at large particles and heavy particles. So first I want to look at large particles, which are larger than eta. Let me just briefly say what we do. We have this Lagrangian, we have this mixer, this French washing machine, and as you will notice in a moment, I want to attract your attention to the fact that this flow is actually quite inhomogeneous and anisotropic, and you have in the middle you have a straining region, but you also have a strong shear. And it might become important when we look at particles in turbulence, because large-scale features might influence the particles, and I say that because I know it does. And otherwise I wouldn't say it. And so what we do is we have this experiment, we have a very bright laser. The particles that we put in are either smaller than the Kolmogorov length scale or approximately the Kolmogorov length scale, they're heavy or light. We can tune that. The amount of investment you have to do is you basically have to buy fast cameras, and you have to buy a bright laser because you need a lot of light to see the particles. And then you have to write a software. And nowadays, I think anybody can do this. It's not something that's very difficult to do anymore because the new cameras now can do a frame rate of 70,000 pictures per second at 256 by 256 resolution, which means you're really getting up there where you can, it's basically the time scale the silicon strip detector had that we were using in 2000. So now the cameras have achieved this, and now of course we can follow multiple particles at a time. So let me just show you. So this was the mixing plate that we used in this mixer. This is about 40 centimeters across. Nowadays we don't use this mixer anymore. It turns out that this one actually, the energy injection scale changed as a function of frequency, and it changed in such a way that if at higher frequency the energy injection rate decreased, which meant that the Reynolds number didn't change. Well, bad luck. And nevertheless, so you can put in 15 kilowatts and you only get as much as you got with the other ones with 2 kilowatts. It didn't make much of a difference. But what you can do is we did R lambda 370 and 460, and the Kolmogorov length scale for this paper, which we published in Physica D, is 61 or 43 micrometers. The time scales are very fast. That's why you need these very high speeds. And what we do now for the next 5 minutes, I will look at polystyrene spheres, which are basically density matched, not perfectly, but almost. And 26 microns is well beyond the Kolmogorov scale. 220 is about, 5 times perhaps. And then we also look at glass particles, which have a density ratio of 2.5, and which are a little bit larger than the Kolmogorov scale. Now, with these flows, the problem is that you need to measure epsilon. And so the question is, how do you determine epsilon in such a flow? And the way we do it is just by using either the second-order structure functions, Eulerian structure functions, or the third-order structure functions. Or we use, actually turns out to be very good measure, is the delta U and delta A as in the Eulerian space, and you average this, and this turns out to be very well. Let me show that to you. So here is for, I forgot what R lambda that is, but probably one of the two cases. And so what you see here is that this is the DNN, this is the DLL, and this is the delta U delta A, which is very nicely flat. So this is what the data is. So this is what we know about epsilon. So we can say epsilon is somewhere between here and there possibly, and we see some scaling. But this is just the data, right? It's like Luca, I'm just showing data. What we of course say is that we fix a straight line here and we call this epsilon. So when we publish data, or every time we publish data, we take this epsilon, we take the fluctuating velocity, and these are the things we know. We know this value here, and we know the fluctuating velocity. But all these measures are, so this is DLL right now, this is the third order structure function, actually goes up. It's not as good usually. It usually ends to be getting worse much earlier in eta than the other structure functions. And I think this is consistent. What you have been showing was R lambda 600. And if I remember your plot, you ended at about 150 eta, everything seemed to end. Or 100 eta. So you would only say that the scaling of this flow might be up to here. So this is actually something we should look at and see why we sometimes see, well, I guess in the second order structure function goes out of course much further, right? It's just the higher order structure functions which if you.
Numeric field, the problem that you are in a periodic, so you must then.
Oh, it's from the periodic problem. So here we don't have that. So, but nevertheless, we get up to 150 or even 200 and 250, which is much further out than the numerics actually goes. Okay, and so what you can do is you can derive just a normal Stokes number, and which is basically given by a Stokes law around the particle, which is Tp over Tf. And what you can do is you can say, well, what happens if I have a particle larger than a Kolmogorov length scale? What that means is that there's what you can assume is that you have a particle diameter, and if you put in this particle diameter, you can calculate the appropriate time scale of the flow, which is just given by the height squared. By the size squared of the particle divided by epsilon to the 1/3. But then what you also realize is that these particles, if they're larger than a Kolmogorov scale, they will also have a Reynolds number greater than 1. And so there's been this paper here where it was estimated what this would be. And you can put this all in, and you can calculate Tp, and then you can say, well, perhaps a better guess of a modified Stokes number would be where you put in the particle diameter over the viscosity to the 4/3. It's a slightly different power law, and then you have this Reynolds number correction, which is weak, so you don't have to worry about it too much. And so what that means is that in our flows, for the particles that are 220 microns and 138 microns glass spheres, so these are the heavy particles, these are the large particles, we get Stokes numbers of order 0.1, and here of order 0.2. So these are really still very small Stokes numbers. And just to show you that the tracer particles do their job, this is the tracer particle experiment for different Reynolds numbers, and this is the measurement that we did with the silicon strip detector, and they agree with each other, and so we concluded that it looks pretty good. You can also look at the higher order moments, measuring with the cameras. That works also quite well, so this looks fine. And so now if you go in and you look at the acceleration distribution function normalized by the variance for the different density particles and the different size particles, you basically get the same curve. So the acceleration distribution function doesn't change, but actually the variance changes, and I know that Jean-François is going to talk about this a little bit more in his talk. And so what we see is, yes, the variance changes, but the PDF doesn't seem to change significantly. You can go a little bit higher in Reynolds number. You could argue that for the heavy particles, the distribution function starts to come in a little bit, but you really have to go down to 10 to the minus 6, 10 to the minus 8 to really see the effect if you want to do that. Now, if you look at the autocorrelation function of acceleration, what's interesting to note is the following. This is the part, it's subtle. So here is the particle acceleration decorrelation, just the normal ones. Now, if you take a large particle, the large particle basically is the red line, which initially decorrelates less, and then it just decorrelates like the passive particle. Nothing happens. From a certain scale on, it doesn't seem to matter anymore whether the particle is time scale on large or not. But for the heavy particle, which I will show again later, you see first that it is slower decaying, so it's basically not probing the flow, it has inertia, but then suddenly it gets swept out into some other region of the flow and it immediately decorrelates. So it's faster decorrelating. And so let me go just to the heavy particles. And so Mathieu has built an experiment. The problem is when you have a French washing machine and it's upright, heavy particles get sucked into the shafts of the propellers and they will never appear again. You lose them very quickly by settling. And so what we built is we built now an experiment that's lying. We have also modified the propellers to different shapes. And so this is Mathieu's experiment. This is like an aquarium where you can just dump the thing in from above. It's much easier than the old design. And of course, we use a laser. And so this is new data, so it's not quite as converged as the other data. And so what you have here is, you see again the plot DNN, DLL, and DU, DA. And so the crosses are DNN, which looks pretty good. DLL also scatters nicely. And DU, DA looks also pretty good. So what you see is, well, definitely it says that this is, this is pretty much epsilon. It's just a measurement. We need a little bit better data. But now the question is, if I now calculate the Stokes number for this particle that we are using, so these particles are 42 microns, which are half the Kolmogorov size, and they're very heavy. They are, no, they are actually roughly the Kolmogorov size, sorry, and they have a density ratio of 4. So the Stokes number for these is about 0.25.
Can you go one back? Why is the fluctuation in N, D and N, so much less? Second order.
D and N always turns out to be the most robust measurement. And the thing is for D and N, okay, so this is an important issue. How are we calculating D and N? Because we have an anisotropic flow where the flow has, the mean velocity changes when I'm sitting at different spots, because I go up to a 4x4 centimeter volume. And so what we can do is, usually you have to subtract the mean velocity. And so for calculating, for example, DLL, we subtract the mean velocity. We have to do that. For D and N, it's not sensitive on subtracting the mean velocity. You get the same result whether you subtract the mean velocity or not. So it could mean that in this case, we haven't resolved the mean velocity well enough yet. We haven't had enough runs to really get a good mean velocity, because it turns out in these flows, we have to make many, many, many runs to get a decent mean velocity. So the fluctuations of the mean velocity is quite large. We have to average a lot to get a good mean velocity. So these flows are actually for a long time are a little bit moved up here, a little bit moved there. So these are not perfect flows, which brings you to the question, how long do you have to average before it's turbulence? Which is a question I think people have been thinking about for a long time. And so what you can do is you get this Stokes number, which is 0.25. And so here what I plot is actually not normalized by the acceleration variance. This is just the bare data. And so what you see here is that the PDF down to the 10 to the minus 6, well, within the accuracy of our measurements so far, doesn't seem to deviate much for the heavy and the light particles. So there was not a very strong reduction in acceleration variance, but as I say, we have to do more measurements to get to 6. But where you see big effects is in the two-particle statistics, and we shouldn't be surprised, because there was a legendary paper by Snyder and Lumley a long time ago, in 1971, and what they did is this was the first particle tracking experiment, and they used copper particles, which were very, very heavy. And what you see is that this is the correlation of the velocity, the autocorrelation of the velocity, and what you see is the heavier the particle, the earlier it decorrelates. And so we can do the same thing in our experiment, and I spare you the velocity. We do this via the velocity structure function because it's less noisy. But if we then calculate the velocity autocorrelation, indeed it decays much faster than for the passive tracers. So this means heavy particles just move very quickly into other regions of the flow and then get thrown apart, and that's why they decorrelate faster. Now again, if we do the autocorrelation of acceleration, what we see is exactly the same behavior. So for the tracer particle is this red curve, which is just like every other curve we have been plotting on tracers before. But then if we have dense particles, heavy particles, what they do is, again, they have inertia, so they respond slower to the flow, but then finally they jump into some other trajectories where a fluid particle would not go, and then it actually decorrelates faster. So this is what it does. Now what we can also do is we can ask ourselves, what is D and N for the particles? So what we do is, since we have particles in the flow, we can ask ourselves, what is the second order velocity structure function for the particles, not for fluid particles, but for real heavy particles. And what we find is that indeed it seems that the heavy particles show a much more larger scaling range. They go to smaller scales than the passive particles do, which would agree perhaps with this decorrelation that the particles get thrown out of the regions that exist in the flow. In the flow, these heavy particles are much more decorrelated than the real particles. But this is what we observe. We can also do this. So what we can ask is, when do these two cross? And so what we can say is there should be a scale-dependent Stokes number. And when we take the scale-dependent Stokes number and so just ask ourselves, where would that be? You know, where do the two curves lie on top of each other again? We find that this is roughly at 0.01. So what that would suggest is if you take a particle which has a Stokes number smaller than 0.01, it behaves almost like a tracer particle. In the liquid, which is also consistent with measurements that we had done before, where we had shown that we had to go down to roughly 0.01 to do a passive tracer. Yes?
The particle are more Kolmogorov.
Yeah, the particles are more Kolmogorov. Yeah. And they go down to smaller scales. They have a different dissipation scale. And so what you can do is you can also calculate the UDA. Now the data again is quite scattered, but again it goes down a little further. I'm almost done. 1 minute, perfect. Okay, so now a lot of talk has been about radial distribution function. Is there a preferential concentration of heavy particles, which would be important for rain? And so of course we would like to know, does that exist for our heavy particles? Now our particles are quite light, I have to say. Stokes number is small. And so we did this experiment, and sure enough, we found that the data for the heavy particle was increasing. So we were quite happy to see that also our particle cluster. But then what we did is we said, well, let's just measure, and I should mention we did the same thing for the light particles. Let's just go in the middle of the apparatus and measure the density, the average density going outward. So how's the number density going from the middle of the apparatus, not from a particle, but from the middle of the apparatus? And if we do that, well, the density is increasing to the middle of the apparatus. So now what we can do is we can take this density relation, just divide out our data from before and just say perhaps it's just a density effect. And you do this, and it's completely flat. There's no preferential concentration at the fast scales, at the mixing scale. On the long time scales, where we average over a long time, yes, indeed, the flow shows preferential concentration, which could still be important for turbulence. And so what you see is that they basically agree, and I stop here and leave 1 minute for discussion.
Thank you. Yes, please.
Yeah, there's one parameter you didn't bring in. You brought in the Stokes number, but there's also the ratio of the fallout velocity to the turbulent velocity.
Right.
It's important in crossing trajectory. So what was that?
I don't have it. It's a density ratio of 4, and it's water. We have to calculate it. It's not that
It
much.
must be having a
It's
significant
not much.
impact.
It's very small for water, because the density difference here is quite low.
But it must be having a significant effect because this effect of Lumley you were showing.
Well, the effect of Lumley, I wouldn't think depends on that number. I don't think it does. In Lumley's experiment, of course, his effect was much larger because he had air and copper particles, which is, of course, very different from water and glass particles. So there's a probably density difference of about 3 or 2 or 3. So I don't know, but yes.
Can I refer back to the plot that you have on the acceleration autocorrelation? You have a couple of those.
On which one?
Someone in the middle, where you show results for particles of different density, where you show them different sizes.
Okay. You mean the different what? The second order structure function?
The autocorrelation function of
Oh, the autocorrelation function, yeah. Of velocity or of acceleration?
of the acceleration.
Yes, here.
Just one, for example. If the density ratio is close to 1 and the particle is small, I suppose you get closer to Lagrangian for particles.
It's this one, yeah, it would be that one.
And I would expect that at small tau it should drop like a parabola instead of linearly, because the signal should be continuous, right? Continuous and differentiable.
Right, you mean that it goes straight
yeah,
to
the-
well, this is, look,
I think
the really
yeah.
small scales you cannot. I
Pardon?
mean, at the really small time scales, right, our experiment, I mean, we probably shouldn't plot it to 0.
Well,
Because there's experimental resolution time scale, right? And down there, you shouldn't take that at Planck value, right? Yes?
well, I'll show more of this.
right?
And also,
So, you know, our time scale is, of course, we have to oversample a factor of 100, the Kolmogorov time scale, to get anything close. And so, you know, the data down here, I wouldn't take too seriously. So it should also be rounded. Yes, I agree. Yeah.
and also, obviously, the area under the wet curve is not equal to 0. So that means the velocity is not stationary in time. Is that right?
But this is because it's got fragmented measurements that are not reconstructed over long enough times.
Yes.
If you do that over longer times, it does.
It comes down. I mean, it comes
goes down,
down.
it oscillates,
Right.
and it goes to 0.
It goes to 0. It actually, I'm actually myself right now a little surprised that it doesn't cross where it's supposed to cross.
It's because it's not long enough.
It's not long enough.
Going
It's
in
gone out
for
for enough
Toida
time.
and all.
Yes.
Thank you again.